Good to go?
Good to go.
All right. Thank you, Chris. All right. Today, the focus of this talk is going to be on phosphorus, particularly dissolved phosphorus. So that's important is when we think about the ways in which phosphorus is transported to surface waters, phosphorus being often the most limiting nutrient in, with regard to surface water eutrophication, with two main forms phosphorus that's transported, particulate phosphorus and dissolved phosphorus. And of those forms, particulate phosphorus is much more easy to prevent its transport. Most of you know, through erosion control practices, we can prevent particulate phosphorus losses. However, the other form of phosphorus transport, dissolved phosphorus, it is a lot more tricky. It's a lot more difficult to keep in one place when soils become very high in soil test P levels. Everybody hear me okay back there? We good? All right. And today, like I said, we're going to be focusing mostly on dissolved phosphorus. At dissolved phosphorus, it's transported basically wherever the water flows, it goes. And most of our standard best management practices, while they work well for particulate phosphorus, they're not nearly as effective with regard to preventing the transport of dissolved phosphorus. And that was the impetus towards the development of phosphorus removal structures. Briefly, though, on particulate and dissolved phosphorus, another issue with dissolved phosphorus, not only is it more difficult to keep contained, it's also a more potent eutrophication agent compared to particulate phosphorus. Again, particulate phosphorus is that phosphorus that it's bound onto soil particles, on the sediments, and when the sediment is transported, the phosphorus bound to it goes with it. And once that particulate phosphorus reaches a surface water body, it may or may not be a problem. It may desorb and go into solution, providing that phosphorus for growing plants and aquatic biota, or it may, that sediment particle may actually adsorb phosphorus from the overlying water column. But on the other hand, dissolved phosphorus, it is immediately available for uptake by aquatic organisms. It makes it much more potent. So the degree of bioavailability of particulate phosphorus is going to vary quite a bit, but dissolved phosphorus, as soon as it hits the water, it's hot, it is ready, it can cause eutrophication problems immediately. So how do we stop dissolved phosphorus from being lost to surface waters? Well, we could broadly categorize this in two main categories: incidental phosphorus losses and legacy phosphorus. So with incidental phosphorus losses, that's the phosphorus that's lost directly through fertilizer manure applications. So through different timing of fertilizer applications, different types of application methods, we can reduce incidental losses. But legacy phosphorus is a bit more tricky. And by legacy phosphorus, I'm referring to soils that get built up very, very high in phosphorus. And even when we do everything else right, we can eliminate erosion 100%. But if those soils are built up in soil test phosphorus, they can continue to leak out a little bit of phosphorus over time. And while phosphorus is mostly immobile, if the soils get built up high enough, a tiny amount will be released with flow events. And that tiny amount is enough to cause eutrophication problems, as you all well know, in the Chesapeake Bay watershed. So we can reduce incidental losses through better management of fertilizer application timing. We can prevent legacy phosphorus sources from occurring through good nutrient management. And if we do have legacy phosphorus occur in our soils where the malic 3 starts to get built up to upwards of 200, 300, 400 milligrams per kilogram and beyond, we can remediate it. And that's the part that I want to focus on today. Again, as far as efficiency goes, we want to prevent soils from becoming legacy sources. So through good nutrient management, managing animal diets, things like phytase enzyme, manure export programs, there are things that we can do very relatively easily, relatively efficiently to prevent soils from becoming a legacy source. If you do get a legacy source, then you've got two things you need to do. You need to contain that legacy phosphorus by managing your flow, certain tillage practices, soil and water amendments, things like that. You can contain it and keep that phosphorus held in the soil to prevent it from being lost, but also we need to remediate it. We need to reduce the legacy phosphorus source. And to do that, the problem with that is it takes many, many years. If you get a soil built up in soil test phosphorus, this example here, this data is actually from Maryland. If you build up your soil test P levels to very high beyond agronomic needs, they tend to stay elevated for a long time. So here we have soils that were brought up all the way up to 600 milligrams per kilogram malic 3, and all phosphorus applications were ceased. We're not even applying phosphorus anymore. And then start the drawdown process. So it was a corn, wheat, beans rotation, and monitor the decrease in soil test phosphorus for years afterwards. And you can see, after many years, the paper published, and now in 2017 they have data beyond 2010. They estimated for soils that are built up around 400 milligrams per kilogram of malic 3 that it'll take at least 20 years to get that back down to agronomic optimum levels. So even when you stop applying the phosphorus, it's going to stay, those legacy sources are going to remain high for a long time. And during that time period, you are going to lose a little bit of phosphorus every time you get a flow event. So phosphorus drawdown, phytoremediation, it's absolutely necessary. It's absolutely necessary for reducing the actual source of legacy P. But again, that's the long-term solution. It's necessary. And so we developed the phosphorus removal structures to try and trap that transported phosphorus in the meantime. So over that 20, 30 years while you're drawing it down and you're still leaking it out, the phosphorus removal structures can help and trap it. So I consider this to be a short-term solution, but needs to be used in combination with phosphorus drawdown to get at the root of the problem. So phosphorus removal structure, and it's very simple. It's just like a filter. It's just like your Brita filter at home. You've got a filter media that has a high affinity for phosphorus, and you take the dissolved phosphorus and it's in the flow. It can be a source of water high in phosphorus from anywhere. Channel it through it and force the water through it, and the phosphorus absorbs to the media. Depending on the media, combined by different mechanisms, and you have clean water go out. It's not rocket science, it's a filter, all right? Designing them, on the other hand, they are engineered structures, a bit more complicated, but the way they work it's really very simple. And depending on the material, you could remove the phosphorus either by ligand exchange mechanisms onto iron and aluminum oxide materials, or some materials that we use to filter the media. We call those media PSMs, phosphorus sorption materials. Some of them are very calcium rich, and they remove phosphorus dominantly by precipitation of the phosphorus as a calcium phosphate. But same thing, in general, you've got a media that has a high affinity for phosphorus, it filters it, you push the water through it, and you retain it. There's three necessary components for a phosphorus sorption, a phosphorus removal structure. They can look a lot of different ways. Very, very diverse, very flexible type of best management practice. But they all have these three components. First of all, the obvious one is they need a filter material. They need a phosphorus sorption material in a sufficient quantity. You have to have enough of it for your site, for your load. And the structure has to be designed such that the high dissolved phosphorus water is able to flow through the material at a sufficient rate. And if you've got a site where you've got 500 gallons per minute flowing through your ditch, your tile drain, or runoff, or whatever, if you can only treat 50 gallons per minute, then you're not going to be able to handle very much of that load. So they need to be designed to handle an appreciable portion of the flow rate. And last, they need to be designed so that you can replace the phosphorus absorption material after it becomes saturated with phosphorus, as you would any filter. And it's designed, you design that with that in mind, to be replaced at a certain time interval. So knowing that, we have a lot of different phosphorus sorption materials, and these structures can look a lot of different ways. I'll give you some examples of that. But first, some examples of different filter materials. There's Some common ones that we like to use around Chesapeake Bay and also in the Western Lake Erie Basin, because they're readily available. A lot of them are, they're byproducts. A lot of them are industrial byproducts. Steel slags, byproduct from the steel industry. Further west, in the Midwest, they like to use sometimes metal filings. Drinking water treatment residuals, byproduct from treating drinking water. Fly ash, gypsum from coal-fired power plants. There are acid mine drainage residuals. There's a lot of different byproduct phosphorus sorption materials. Not all of them are equal, and not all of them are necessarily safe. They have to be screened prior to use to make sure that they're safe for mostly things like trace metals. There's also some filter materials for phosphorus that are manufactured, and some of those, they do work very well. They tend to be extremely efficient on a per mass basis, but they're also very, very expensive as well. In fact, most of them are cost limiting. Probably the cheapest one is a material known as phosphoridine. Some of these materials, particularly the ones that are made out of iron and aluminum oxides and hydroxides, they have potential for being regenerated. And this is something we're continuing to do research right now in our laboratory in West Lafayette. But in a normal scenario, we have phosphorus flowing into our iron-rich material. We absorb the phosphorus through a ligand exchange mechanism. And then once it becomes saturated with phosphorus, we can strip it off with a hydroxide solution of some sort, regenerating it, getting it ready to reuse it again and again. And with that phosphorus that we strip out of it, we can potentially precipitate it as a calcium phosphate. Is this something viable to keep using as a fertilizer? Yeah, you could, but it is not necessarily economically viable. It is viable to strip this for the purpose of reusing it again, not for the purpose of getting a fertilizer. And it's mainly because of the paradox between the amount of phosphorus that's being lost from terrestrial surfaces, from ag land and urban land, versus the amount of phosphorus needed to grow plants in those spaces. It's a huge dichotomy, or a huge paradox, which is why we have this issue of phosphorus in the first place. We need so much in the terrestrial landscape to grow crops, but a tiny bit of it leaking out, reaching aquatic systems, is causing a problem. So we can apply this technology in a lot of different settings: urban settings, rural settings, wastewater. Basically, anywhere you have a concentrated flow high concentrations of dissolved phosphorus. And this isn't just an agricultural issue, it's an urban issue as well. Wastewater treatment, we can use these in wastewater treatment as well. Especially, we could use them in small domestic systems, home systems, and also for small wastewater treatment plants. This is one wastewater treatment plant in New Zealand, I believe. It uses steel slag as a tertiary process to strip the dissolved phosphorus from it. Also wastewater from agricultural uses, lagoons, dairy lagoons, swine lagoons. This is a structure located in Maryland, constructed by, I believe this one was, I think Drew Coslow and Tim Rosen did this one. But essentially they have a lagoon that they settle out the solids, and they send it through a phosphorus removal structure that's treated slag in it, and then from there it goes on to a wood chip bioreactor to remove nitrogen. So a lot of flexibility. We can use these things in a lot of different places. Manure and silage storage areas. Anywhere you have high concentrations of phosphorus that can potentially leave a site in concentrated flow, where you can channel that flow into one location and put it into a phosphorus removal structure. Greenhouse and horticultural situations. Here's one. This is a small filter we built in a greenhouse at Purdue, where we treat all the phosphorus, the excess water that drains out of the pots. So these structures, they can look a lot of different ways, but as long as they have those three main components, it's a phosphorus removal structure. And every site's unique. So some of you, if you have a site that you're picturing in your mind, you can adapt this in different ways. Again, as long as you consider those three main components. I'll give you some examples. Before I show you some examples, one thing I will say is this is not a best management practice for sediment, for erosion. All right, we have lots of best management practices for erosion that are much, much cheaper and easier to use than this. And allowing a lot of sediment to flow into these things can cause problems. This is one from a ditch filter we built in western Ohio near Grand Lake St. Mary's. And there was so much sediment loading into it from the ditch eroding that we had a kind of a premature failure of the filter. It was designed to last several years, and it's not performing as it should because of this. So you need to take care of the easy stuff first, take care of the sediment. One type style of structure is the cartridge filter. And this is what everybody wishes the phosphorus removal structure could be. They envision in their minds these nice little cartridges we can plug on the end of a towel drain or something like that. And that's nice in theory, but because they're portable, they're easy to install. The problem is it only works in limited situations. And look at the size of these things. Something like this only holds a couple kilograms of material. If you consider the load of phosphorus leaving your field, do the math. It's going to take a lot more material to remove that phosphorus than just a few pounds, unless you want to go out and change it several times during an actual flow event. So it's nice in theory, but these cartridge filters only work in very limited situations because they have a limited amount of phosphorus sorption material. Another style is the confined bed, like these ones, especially for capturing surface runoff. It's good for a large filter area and to build into drainage swales that have very high peak flows and non-restricted drainage. And so you achieve that through a very shallow bed of a phosphorus sorption material spread out with subsurface. Here we have the inlet of this culvert. This one is located on the golf course in Oklahoma. We have subsurface drainage pipes right at the surface, just below the slag here. It distributes the water that drains down through that slag, is filtered, and then goes out through that drain pipe right there. We have an overflow weir. We built several confined beds style structures. Ditch filters, we've built a lot of these in Maryland. In fact, I bet that probably several of you in this room have contributed one way to another. Dr. McGrath done, I'd say probably at least maybe 15 of these structures in Maryland. Similar to a bed filter, but without confinement. You don't have to build a box around it. You've already confined through the ditch itself. And you've got your buried perforated pipe backfilled with your phosphorus sorption material. And it allows a large amount of material to be used. Often these will have around nearly 100 tons of material. And there's what it looks like. We use a flow control structure to maintain head on it. Water flows down the ditch and drains straight through the material where it's filtered and then back out around to another ditch. We've built a lot of those. Generally low cost because you've already got the ditch in place to hold everything in place. Box filter. This is kind of a glorified cartridge filter, except it's much larger. This was built on a farm in Maryland as well. We can easily switch out the materials with this modular design where you can take the boxes out, pull them out, replace them, clean them out, and set a new fresh one in. This particular unit drains this pond that captures all the surface runoff from this poultry farm. And in order for that water to leave the pond, it has to flow through these perforated boxes full of phosphorus sorption material. They work great for small ditches or for pond overflow, but if there's any drawback to it is it's a relatively small amount of material. There's only about maybe 1,000 pounds of phosphorus sorption material in each one of those, which for some phosphorus sorption materials, that's sufficient, but not all phosphorus sorption materials are equal. Some are extremely efficient, some are not. I'll give some examples of that later. Blind inlets. I don't know how familiar you are with blind inlets. This is something that's popular in the Midwest, but blind inlets are constructed in kind of low-lying or small depressions in relatively flat areas where water tends to accumulate and pond. Traditionally, they put riser pipes in the field to drain those. One alternative is to build a blind inlet to capture all that sediment. Usually, they use limestone gravel to filter that water out. It's mostly to remove sediment. It doesn't remove phosphorus. But if you replace that, fill that with a phosphorus sorption material instead of just regular gravel, you can get additional benefit of removing dissolved phosphorus. It becomes a phosphorus removal structure. Here's one being constructed. You can see the drainage, perforated drain underneath it, and here it's being backfilled with is backfilled with slag, and this is the final product. Tile drains, we can build tile drain filters. They're basically an underground bed where the tile drain must flow through a bed of phosphorus sorption materials before it can drain out into a ditch. And we can design these, we can design all the structures to flow either from the top down through the media or flow from the bottom up through the media, depending on the situation and how much hydraulic head that we have available at a site. Here's an example of a tile drain filter. This is one that's just about to be buried. This is the top of it where water flows inlet from the tile drain. We got a flow control structure to control the head and the flow rate. And we have this drainage manifold to spread the water out. It drains down through a foot or so of the sorption media, and there's another drainage layer, or another drainage pipe layer, I should say, to capture that and take it to the ditch. They're not much to look at once they're completed because they're buried. But this is in being built. That's what we have. Bioretention cells. These are popular in urban areas. Very, very similar to the blind inlets. If we replace the soil in a bioretention cell with a phosphorus sorption media, then in effect it becomes a phosphorus removal structure. Same thing. You have a media set up. Water must infiltrate through it and is filters the phosphorus before it reaches a drain. This is what they look like when they're completed. They also serve the purpose of buffering stormwater flow. So they can look a lot of different ways. We can design them each site is unique, very flexible design, but where should we put them? And some people look at it, they want to stick them on every single tile drain, or they want to put them anywhere where they see concentrated runoff. But in order to be most efficient with this, because this is a last ditch effort for a BMP. This is not something you just want to put everywhere. They're not cheap. All right, this is what you do on the far end after you failed at preventing legacy P buildup and containing it. So you don't want to put them everywhere. You want to put them only at the hot spots. Only where you have the highest dissolved phosphorus concentrations, because it's the most efficient. It's the most efficient thermodynamically, it's the most efficient economically. And you also want to put them in places that are hydrologically connected. If the flow if it's not very likely for the flow to ever reach a surface water body, then it's probably not worth building a structure there. You also want to put them in places where water converges to a single point. Remember, you got to get the water to flow through the media. Just water just skimming over the top of a filter media, that's not going to cut it. That doesn't work. You have to force the water through the media. You need site that has sufficient space and hydraulic head. It takes gravity. These are all gravity driven. So you need hydraulic head to push the water through these at a sufficient rate. It's not uncommon to see sites like this in the Midwest, where here you've got a drainage ditch and all these tile drains. And people ask, well, what are we supposed to do? Put one on every tile drain? No. Only build a structure on the hot spots, only in the hottest ones. Here's an example. In Florida, they've proposed to build phosphorus removal structures on these giant canals. And their phosphorus concentrations in these canals are very low. Most of the phosphorus, while it may be high relative to aquatic life, for removing it, it's pretty low. And so they want to build these giant filters on these canals. It's not a very good idea. The P concentrations are so low, it's not very efficient. Let's take an example. This non-hot spot. Picture this canal. I'm making these numbers up as far as flow. Say it's 1 million gallons a day of flow, and it's 0.01 parts per million phosphorus. So that load, that's about 0.085 pounds of dissolved phosphorus a day. All right? Consider this. Here's a drainage ditch. Much smaller flow. Let's say it's only 100,000 gallons per day, but the concentration is 0.3 parts per million dissolved phosphorus. Now that one's pumping out about 0.25 quarter pound of dissolved phosphorus per day. So which one is going to be more efficient to target? Here we've got a higher concentration, and you only have to handle 1/10 of the flow rate compared to that canal. It's much easier and more efficient to go after your higher concentrated flows and lower flow rates. You know, move up in the watershed to get, the closer you can get to the hot spots, the more efficient it'll be. You don't want to treat them after those converge. Some people say, oh, let's just wait till it all hits a ditch or a river and treat it then. No, it's same problem. It's not very efficient. You want to treat it while it's still hot. Take this example. If they converged, if that drainage ditch converged with that canal, in theory it'd be 1.1 million gallons per day. The concentration would be 0.36 parts per million and 0.335 pounds per day. 75% of your dissolved P load is found in the more treatable hotspot of only 100,000 gallons per day. Much, much more efficient to go after those hotspots that are smaller than it is the more dilute ones. Just thermodynamically speaking, phosphorus sorption materials work better with a higher concentration. It gives it a higher chemical potential to push those reactions to remove phosphorus. So be very careful in choosing these locations. I consider it a form of precision conservation. You want to choose your locations very carefully to get the most out of it because it's not cheap. So how long do they last? How long do they last and how much phosphorus will they remove? So everybody wants to know. Well, the short answer is it depends. What do you design it for? It'll perform for whatever you design it for, assuming you design it properly. It depends on the site conditions. What kind of flow rates do you have? What kind of total flow volumes do you have? What's your phosphorus concentrations at the site? How much material did you use? How was it designed? What's the retention time for your structure? All these things are very important in dictating how to design it and how it will perform. But I will give you an example. This is from a review paper we recently published where we gathered up all the 40 different studies of phosphorus removal structures at the field scale and at the pilot scale. We excluded lab studies, and we separated them into wastewater and non-point source runoff. Now, again, I hate to give just a blank number for performance because the truth is they perform however you design it for. I can design one for you that'll remove 50% over 10 years or 30% over 2 years. Whatever we design it for, it may not be feasible, but again, it depends on what you design it for. But just to give you an example, wastewater, depending on what type of material you're using, I broke them up into different categories. There's wastewater using sand and shale. It's mostly going to be biological removal, not sorption. Wastewater using calcium-rich materials as the filter material, and wastewater using slag. Slag is a calcium-rich material, but it gets its own special category because there's so many structures built with it. And wastewater using mine drainage residuals and iron-rich materials. Those wastewater tends to remove, those filters with wastewater tend to remove more phosphorus than with non-point. And the reason why is because with wastewater, you've got much higher concentrations of phosphorus. It makes it more efficient. It's hotter. And you have a much longer retention time. Retention times for wastewater, usually you can have them for hours to days. For non-point, we have so much flow, such high flow rates, hundreds of gallons per minute. Our retention times are often from seconds to minutes. So we don't have that luxury of many days, although we try to design them for the longest retention time possible. So if you want an overall average for non-point, it tends to hover around 30%. That's cumulative removal over its entire lifetime until it needs to be replaced. So how do we design these things? Well, we developed some software when I was at Oklahoma State. It's called Phrog, Phosphorus Removal Online Guidance, which is available in Maryland. There are several people who have the software and have used it to construct structures. In fact, that one on the farm in Kent County, they used Phrog to design that structure. But as far as the inputs go, we use it we gather site inputs, obviously, hydrology. You need to know something about the peak flow rate at your site. What's the peak flow rate that you want to be able to handle? Do you want your structure to be able to handle 100 gallons per minute, 1,000 gallons per minute? You want to be able to handle something close to the peak rate because that's when you lose most of your phosphorus. You need to know something about your annual flow volume because that dictates your load of phosphorus, right? And obviously, this is all phosphorus concentration. Those two things together, concentration and total annual volume, dictates that's your load. And your max footprint. How much area are you willing to give up to build the structure? And then there's some inputs as far as your desired lifetime. How long do you want it to last, and for what removal rate? So it's cumulative removal. Oftentimes I usually design them for, it depends on the site because some things aren't feasible, 40% cumulative removal over 5 years. So that means 40% of all the phosphorus that's going to flow through this location over the next 5 years, I want to trap it right here in this media. Other sites, I can design it for longer. Others have to be shorter depending on the feasibility of it. And we need to know something about the filter media itself, the P-sorption capability of it and its physical properties, because remember, we have to be able to push water through it, and also the safety, need to characterize for safety. So we plug all this in, and we get the output for design parameters. What mass of that particular phosphosorption material do you need to meet those goals, those removal goals, for your particular site? What mass do you need? What area does it need to encompass? What depth does it need to be? And what's the pipe requirement to be able to handle those desired flow rates? And we have this set up for specifically for doing beds or ditch. Because ditches are a bit unique hydrologically, so we have a special set of algorithms for that. We can also run this backwards. Let's say you build a structure kind of blindly and say, I'm just going to, whatever I can build, I'm just going to put it out there. Well, we can run it backwards, and you take the characteristics of your structure, plug it in, take the characteristics of the site, and the software will tell you, all right, this is what you built, it's going to last X number of years, and it's going to remove this much phosphorus over that amount of time. I'll give you some examples on that in a second here. Here's one we built at a poultry farm in Oklahoma. There's about 16 poultry houses, a lot of spillage of litter outside of them. Flow direction goes to the north, right up into Green Creek. So we built a structure right here, channeled the flow into it with berms. And we built the structure right here using steel slag. And this particular structure, so this is confined bed style. You can see here's a berm. There's a berm over here off the picture. Up here are the poultry houses. Water converges into the unit. We have perforated pipes to distribute the water over the unit, drains down through and out. This particular unit removes 7.5 pounds of dissolved phosphorus in 2.5 years. It was 23% of the 2.5-year load. It's still removing phosphorus. It's still effective. And as far as flow rates go, it has handled about 1,000 gallons per minute of flow. It's handled everything that it's seen so far, and we've had some pretty hefty storms since we installed it. Here's an example of one single storm. This was in June of 2014. Here's the hydrograph. We hit nearly about 700 gallons per minute, and in that single flow event, there was about half a pound, a little over half a pound of phosphorus, dissolved phosphorus, that flowed into that unit in one event. And in that single event, we removed about 0.33 pounds of the phosphorus that flowed into it. Here's a bioretention cell in an urban area. This is in northeastern Oklahoma. They used a sand fly ash mixture as their phosphorus sorption material. And based on the flow that was going into it and the amount of media that they used and its characteristics, it'll last about 67 years. So again, the short answer is performances, it depends. And we can design them to last for however long you want. And to do that, we have the Phrog software. Additional support, there is a interim NRCS standard for cost share. It's standard number 782 if you're interested in that. I'm not sure if Maryland, I think Maryland has adopted it. Delaware might. Other states are looking at it right now. I think Wisconsin has adopted it. Maybe some others. Quick example of the software inputs. A little more detail on that. Let's take a site here. I'll use a ditch since we're in Maryland. A lot of the drainage here is through surface runoff ditches. So one thing you have some idea about is annual flow volume and your dissolved phosphorus concentration. That lets you know your annual phosphorus load. Second thing you need to know is specific of flow rates. What kind of flow rates is this ditch going to see that you want to be able to handle? What's the size of the ditch? Obviously that's going to be pretty important for a ditch structure. You need to know the dimensions of it. What's the maximum length of the ditch that you're willing to give up to build the structure? What diameter of pipe do you want to use? This is something you can play with on the software to optimize your design. What are the chemical and physical characteristics of your filter material, the PSM? Plug in your desired retention time. That's only relevant to certain PSMs. What's your desired removal and lifetime? How much phosphorus do you want to remove over what amount of time? And optional, it will predict how much total phosphorus and sediment can be removed if you put in some additional inputs. And this being a ditch, remember that ditch was built there for a reason, to convey water. So you need to be careful and consider, remember you're putting solid material in it. So by putting a filter media in it, you are going to, by default, decrease the flow capacity of that ditch. You don't want to decrease it too much. You don't want to flood anybody upstream, right? So one of the inputs is you're given that choice of what percentage of the ditch flow capacity are you willing to sacrifice to build this structure. So we'll do an example right here. Input, we put our phosphorus, the characteristics of our phosphorus sorption material, chemical characteristics, or we can put in a phosphorus removal curve. Details I'm not going to go into. When we can do that, we can directly measure that. Physical characteristics, bulk density, porosity, hydraulic conductivity, site characteristics and goals. For this particular example, we're using a kind of a medium to low quality steel slag. We're going to specify a desired retention time of 10 minutes. We want that water being in contact with slag for 10 minutes. The average dissolved P concentration of this ditch site, I'm going to say is 0.5 milligrams per liter. 1 million gallons per year flows through that site, and we want to remove 40% of the 5-year load. We want to use 4-inch diameter pipe, and it's going to be set at a slope of 0.5%. We want it to be able to handle 400 gallons per minute, and we're only willing to give up 20% of the ditch flow capacity and give up a maximum of 250 feet length of ditch. The ditch is 12 feet wide at the top, 6 feet at the bottom, 5 foot deep. And the slope of the ditch is pretty much flat. Manning's roughness coefficient, we're going to say this is a grass ditch. So we put in our appropriate Manning's coefficient, and we get our output. Required mass of PSM, the required depth of the PSM, the length, required length, number of pipe, cumulative removal with time, maximum flow rate, actual retention time, percent loss, and ditch flow capacity. Here's the output. So for this particular scenario, it's going to take 100 tons of that specific slag at 17 inches deep, spread out over about around 200 feet long. We're going to need 8 of our drainage pipe. It's 4-inch diameter we specified. Need 8 of them. And we met all our goals. Our retention time is over 10 minutes, so we're good. We met our flow rate goal. We're over 400 gallons per minute. We're good. And we're less than 20% for decrease in ditch flow capacity. And here's our phosphorus removal. We met our goal. Remember, it was 5 years, 40% cumulative removal, which is around 8 pounds of phosphorus removal. And this is how long it will last. So it'll last about 10 years until it's no longer effective. And we have a nice table showing how much phosphorus we'll remove through that time. So it works really nice for nutrient credit trading, if that was ever to happen. Give you a quick example of what happens, the variation between different types of materials, even with slag. This is a very, very high quality slag I discovered happened to find at one of the plants in Indiana. I call it a super slag because with only 80 tons, I can remove 70% of the 110-year goal. This stuff is much, much more efficient to remove phosphorus. And remove a lot of pounds of phosphorus in that amount of time. So we have we validated the model, and it's not perfect, but it works pretty good. This is through the characterization of the media, chemical characterization. If we directly measure the phosphorus removal, it's even better. Economics, similar to the design and performance, it's going to depend. The initial cost is the greatest. You need to be able to retain that PSM, but once you build that, your main cost is going to be in the clean out. The clean out for maintenance depending on what you schedule it for. But the average cost per pound of phosphorus removed decreases with time because of that. Like I said before, they're not cheap to build. It's a last ditch effort, So I consider it a form of remediation. But it's justified, the cost is justified, and that dissolved P is much more difficult to remove compared to particulate phosphorus, and it's much more potent as a eutrophication agent. Our structures cost generally between $5,000 to $12,000 to build, and I give people a wide range. I use the scale of, I speak in the language of wastewater treatment plants. They value phosphorus removal per pound of phosphorus removed. It costs them anywhere between $50 to $800 per pound of phosphorus. That's total phosphorus removed. It's going to be similar for dissolved phosphorus removal for these structures. So we're in the same ballpark as the wastewater treatment structures. But it's going to vary. It highly varies, as you can see. Some different cost of removing total phosphorus. In the Twin Cities, this is analysis. This is cost per pound of phosphorus removed. But again, that's for total phosphorus. That's not for dissolved phosphorus. Dissolved phosphorus is worth a lot more to remove for those reasons that I mentioned. It's much more potent eutrophication agent, and it's just much more difficult to remove. And look no further than the example of the Western Lake Erie Basin, Toledo. They shut down their drinking water treatment plant. It cost them estimated $40 million in 1 week. Okay, trying to leave a little bit of time here for questions. A lot of people I'd like to thank, probably a lot of them are in the room that I've just never met in person, but we've got a lot of this research started here in Maryland with Dr. McGrath, and there were a lot of different groups that helped provide funding for us to build these demonstration structures. You know who you are. And especially I'd like to thank Dr. McGrath for helping to get this going as well. We started on this, gosh, it's been 13 years now, I think. He no longer works on this, but I couldn't have done it without him. There is a book available to provides all this information to help you in being able to actually design and construct one, and some information online. So, talked too long here. Do we have any time for questions?
We do. Let's give our speaker a hand real quick. I know there have to be a handful of questions out there. Sally, go ahead.
Mine's an easy one. What's the name of the NRCS configuration practice standard?
It's number 782. I can't remember the name of it. It might just be called phosphorus removal structure, dissolved phosphorus removal. Phosphorus removal system, 782.
Are you familiar with Conowingo and Chesapeake Bay Dam?
I've driven over the dam. It's been years.
Okay.
I'm from Pennsylvania.
So there's 100 years worth of sediment behind the dam to put from the top.
Yeah.
What's the solution other than dredging?
For lakes, I consider it similar to, analogous to a lake. People will treat the lakes and areas like that with alum, things like that, and it'll tie up the phosphorus temporarily. That's the issue. You would have to keep treating it after it no longer becomes effective, because as you know, that phosphorus, you can tie it up in a lake, a reservoir of some sort, but it's still there. Other than dredging it, dredging it will really get to the root of the problem. I don't know if it's possible. I've always wondered if it's possible to cap them. I don't know what the effective depth is of the sediment that contributes nutrients to the overlying column. I don't know if it could be covered up with, lack of better terms, clean soil.
If you did dredge it, is stirring it up making it work?
Yeah, see, that's the other thing. Dredging has a whole host of other issues in itself. As far as that balance, I don't know. I don't have a good answer for that. It's a good question. It's an important issue.
Out of the different sorption materials we talked about, which ones would you say are the cheapest?
Cheapest ones are free. Usually, there's a catch to them though. You have to transport them. Steel slag, and again, they vary in quality. You can get some really, really good steel slag, and it can conduct water through it real fast. But it may take a lot of tons, so it may cost a decent amount of money to get it there. We do have treatment processes for the slag to make it more effective, and we can recharge it a couple times, but not infinitely. Take something like drinking water treatment residuals. They can be more effective on a per mass basis. You won't need as many tons often, but it's very difficult to get water to flow through it. So you got to consider that in your design. You may have to take a larger area because the hydraulic connectivity is less. So that's one of the reasons why we made that software. So you can plug in different types of sorption media for your site and look at all the different options of what a filter might look like and then do your economic analysis. But my favorite are iron and aluminum rich materials because they tend to be more efficient on a per mass basis. Acid mine drainage residuals are my favorite because you can get them for free and you don't need as much of them because they're so efficient on a per mass basis.
How about heavy metals with those materials and testing?
Yep, testing. So I recommend, I test everything. There's a chapter in that book on that, or section in the book on testing with methods, and particularly for safety. Test for total metals and also for solubility of metals, not only in water, but also in dilute acids. Going after the worst case scenario to see if there would be any potential release of metals. All my structures, all my materials, before I put them out in the field, I test them for all these things, and then even when they're out there, I still test them for metals to make sure I don't have anything. And so far, everything's been clean. Yes, sir.
What's the pH of the water coming out of the system? Speak up. Again.
pH of the water coming out of the system. It depends on the phosphorus sorption material. A lot of the byproducts are near neutral. So you have near neutral water coming out. Some of the materials are alkaline, and so the pH of the water coming out can be elevated up into the 9s. But even though the pH of it may be elevated, don't let the pH alone fool you. You have to remember what's more important is the total alkalinity, the ability of that water, of that drainage water, to change the pH of the system. I always use the example of on the flip side of acidity. You have titratable acidity. You drink a pop, drink a Coke or something. The pH of it is around like 3.5. But you pour it on your tongue, pour it on your skin. It doesn't dissolve anything. It's not. The pH of it may be low, or the pH of something else may be high, like toothpaste. But if it's not highly buffered, it's not necessarily a problem. So what's more important is to consider the alkalinity or the titratable acidity, depending on which end your phosphorus sorption material is. Slag, normal slag can have a high pH coming out, but it doesn't have very much alkalinity. We had give you an example of that. We had a pond, a very small closed pond that we would filter water through continuously. There was no outlet to this pond. All the water was filtered through our slag, and the drainage water coming out would have a pH of around 9, sometimes up to 10, but it never changed the pH of that pond, even though it was a closed system, just to show that while the pH may be elevated, alkalinity and buffer capacity is critical. Good question.
Any more? I know you're from Pennsylvania because you drink pop, right?
That's right. Yeah. I'm from west of the Allegheny Plateau in Appalachia, so we call it pop. So.
All right. Thank you, Chad. Let's give him a hand.
Thank y'all. Thanks for the heads up. I'll go.